So switching to English, let's continue. Now we got to our third block, and here, we still continue talking about systems and programming and complicated architectures, etc. So our next speaker is Dmitry Duka. He is a senior manager at Omniverse, the Nucleus project at NVIDIA. He is specializing in programming, graphics programming, high-performance computing, and system design. He's going to talk about NVIDIA Omniverse, a dive into the server infrastructure. Please welcome.
Hello, everyone. I'll be speaking English since I don't know Armenian nearly well enough to deliver a lecture. I hope it'll become better with time. Anyway, so let me introduce myself first. I joined NVIDIA in 2010 as a software engineer, and I was working mostly on PhysX, our physics simulation library. With time, I became team lead of the group that was working on a library called Apex, which is a library on top of PhysX, making it much easier to use relatively low-level libraries such as PhysX for game developers and other users. My other important for me project was Ansel. It is quite a successful project for NVIDIA. It's a special screenshot kind of game photography tool where we can take special types of screenshots like 360s or very high resolution screenshots like tens of thousands of pixels wide. We did a lot of interesting things there, including AI, virtual photogrammetry. We did a lot of integrations with popular games, and that was quite an exciting project for me. But starting 2018, I think, I started working on the Omniverse platform, in particular, I helped to jumpstart the Nucleus, which we're going to be talking about today. As well as Carbonite, which is kind of like mini Qt library for Omniverse. It's like a foundational framework on top of the entire Omniverse is built. Now the agenda shortly for today is going to be Omniverse. Then we will dive deeper into Nucleus, which is the server infrastructure that I and my team are working on. We're going to talk about the general principles of the Nucleus architecture. And then we're going to be mostly talking today about asynchronous programming that's happening inside Nucleus. Since it's a server, it is heavily asynchronous. So first, let me tell you very briefly about what Omniverse is. So Omniverse is put very shortly, a Google Documents for 3D scenes of any size. That's the most short definition that I can come up with. So if we try to find what are the components of Omniverse, I would say there are really three main components. One of them is our general purpose renderer, and when I say general purpose, I mean that it works on clients, it works on the servers, it can scale with many servers and work on the same scene in a distributed environment. It works on Windows and Linux. Of course, it's ray traced, uses CUDA, state-of-the-art algorithms for denoising and whatnot. The other pillar on top of Omniverse stands is USD. We believe USD is the language of 3D internet in the future. You know, they talk about metaverse, it's a hypey topic. No one knows what it's going to be, but we believe that if it is going to be true, then there must be a common language. Like HTTP is such a language for the internet, so is USD for exchanging 3D information. And finally, the data hub, which is largely Nucleus. That's what my team is building. It's this common part, the server that unifies all technologies together. That's what makes it possible to connect AI and physics and ray tracing and any other technologies together into this single platform. I'd like to show you a couple of videos just to get you kind of look and feel of what Omniverse is visually. So we can see how different technologies like Flex in this case, simulation of soft bodies, of rigid bodies, all come together with great ray tracing, with AI. Customers outside of NVIDIA, such as researchers, for example, use our technologies within Omniverse to simulate weather, to simulate outer space. Omniverse is being used to model production of cars, for example, like BMW factories are all now built inside Omniverse first before actually building them in reality, because it's much more efficient, economically speaking, to model what you're going to build first and find all the possible mistakes and then not do them in reality. The second video that I would like to show you is about collaborative aspect of Omniverse. We can see here 4 different people working on 4 different machines for different workstations. They're all working really on the same scene. And each one is doing his own thing. Like one of them is working on the interior, another one is on the lighting, the third one is working on what surrounds the whole building, etc. And the most important thing here is that it's all happening in real time, which makes this whole process of modeling the building, in this case, much more efficient and generally much faster. So just a couple of more pictures before we dive into technicalities. This is our web client. This is basically, it's called Navigator, Omniverse Navigator. It runs in the browser. It runs as a separate Electron application. But it is what GitLab is to Git. But this is what GitLab is to Git is to our Nucleus server. And this is what we call Omniverse Create. It's kind of like Maya style application where all the NVIDIA technologies are combined together. This is where the ray tracer I mentioned is being used also. This is the main tool that artists inside and outside NVIDIA use to work on the scenes. Now, below, you can see the file selected, and this is the view to Nucleus. This is the view not to the file system, but actually to the server that we are going to talk about today. So what are the challenges of the Nucleus design? I would say there are 2 main challenges. The first one is that we have to support wildly different deployments. So we have to build both native binaries and containers as kind of like artifacts of our code base. We have to also run on workstation, on-prem, and in the cloud. And all of this must be supported by the same code base. Now, usually when people build file storages like that, generally it's possible to pin down dependencies better. But in our case, we unfortunately have to support all these platforms. And there is a reason for that. So we have to support workstations simply because you cannot ask an artist to work on containers and Kubernetes and talking to DevOps engineers to maintain all of this. So we have to run maybe in a limited fashion, but we have to run still on workstation. And what I mean, literally as native binaries on Windows as EXEs, on Linux as just Linux ELF binaries. with a tiny icon in your system tray where you can manage all the services and still use them and basically connect to localhost. The reason to support on-premise deployment is because a lot of customers actually cannot put their content to the cloud. Let's say Disney. They will never put their content, their assets for the upcoming movie to Amazon, for example, because one leak is enough to cancel the entire movie. And finally, we need to support the cloud because for those clients who can trust clouds, it's just much more, it's much easier, it's much faster to get started with the platform. So our architecture, how we architect Nucleus, is largely modeled after this law. We really embrace this law, which states that any software largely represents the organizational structure of the people who are building the software, right? So if you have many disparate teams across the globe, such as we are at NVIDIA, we have many offices across the planet, we decided early on that we will just embrace it, and we will live in like different pieces of Omniverse. We'll live in different repositories, maintained by different people, maybe even with slightly different CI approaches, different tool chains, different languages, etc. And yet, we still have to somehow interoperate efficiently. And so, because of that, our architecture is module-based, and Nucleus API in particular consists of many modules because we have to work differently on workstation compared to the cloud, let's say. So, for example, just to really pin this point down. In the cloud, we would rather prefer store the actual content, like bytes of those textures and models and whatnot, in something like Amazon S3. It scales, it works great in Amazon, etc. But on workstation, of course, there is no S3. There is a file system. And so we have to change the Nucleus configuration such that it uses the file system to store the content. Same thing happens with key value storage, because the data, the way Nucleus stores data is basically we need to understand how we store metadata about a particular piece of data and the data itself. Now, I touched already on the data, but metadata is pieces of information like timestamps, who created the file, ACLs, the file name itself, etc. And so we store it in the key value storage. Again, on workstation, we could use something like LevelDB, which is an embedded database, very fast, but absolutely not scalable. But on the other hand, on workstation, we don't need to scale. Now, in the cloud, LevelDB is not an option because we have too many users concurrently, and LevelDB, even though it's quite fast, will not do. And in that case, we would use something like DynamoDB or Redis or something like that. And the method to achieve this kind of flexibility, that the same code base offers all of these possibilities, and you just change configuration file and deploy in a particular environment, is to use the Carbonite. So the Carbonite is this thing that I mentioned. It's the framework that manages all these modules that we implement. And one of the architectural principles we maintain is we have to be really careful about the interfaces. If you need to design the interface, you have to first see at least 3 possible implementations and verify that the interface is satisfiable by all these 3 implementations. The other principle that we are employing is related tightly to the fact that C++ unfortunately doesn't have stable ABI. So what I mean here is if you happen to use something like std string, for example, at the boundary of your module, which is on Windows, it's really just a DLL. If you happen to use something like std string at the boundary of your module interface, what you're risking in this environment where different teams using different tool chains may consume your module, and if they happen to use a different tool chain, they may have very interesting and very time-consuming bugs. Where in the worst case, in the best case, it will simply crash, but in the worst case, it will not crash, and it will continue to work until it will crash very mysteriously, and you will find yourself in the middle of a 5-hour-long debug session. So we avoid any binary effect in C++ types and constructs at the boundary of the interface, but of course we use C++ widely inside the module. So as I said, yeah, it is based on the carbonites. Here's an example of the interface where we can still use some C++ isms in the interface, but we have them listed, what can be used. In particular, for example, enum classes, like the type-restricted enums, can be used. Boolean values can be used. References can be used just because the ABI for those things never change in practice. But for, again, types like STL types, this is unfortunately not true, and so we have to use C types at the interface. Now, the final topic that I wanted to touch upon is each module, let's say, a JSON serialization module may decide internally to use a library like Boost, for example, for whatever reason. Now, what we decided early was also to avoid linking to these libraries, especially to popular libraries such as Boost, OpenSSL, zlib, and similar libraries, to link them dynamically. Because remember, all of these teams across NVIDIA, they come up each with their Carbonite module with very carefully thought through interface. And this whole thing is designed to cooperate together, to be easily combinable, so that whoever wants to build an application can get the module for ray tracing, and the module for AI denoising, and the module for configuration and for logging, and combine all of this easily together. And if each module, like literally again DLL, comes with its own set of DLL dependencies, what will happen in the end is in the final application you will have the same third-party dependency in multiple versions, and we really wanted to avoid that because it typically is very hard to manage. So we embrace static linking in this case, so that each module is self-sufficient as much as possible. Now, these were our main architectural principles of what we are doing to enable different disparate teams to still work together and reuse all these results efficiently. Now I'm going to switch to principles of asynchronous programming that we employ in Nucleus specifically. Nucleus is one of the most asynchronous pieces of software, I would say, in Omniverse, just because it's the server that has to handle hundreds, sometimes thousands of clients working simultaneously with the server, and the server itself needs to asynchronously talk to the key value storage, asynchronously talk to the data storage, sometimes asynchronously talking to other services, and we have to somehow maintain the code base manageable, because asynchronous programming is actually not that easy to make both efficient and easily understandable by developers who are working on the project. But first, just a basic brief on what asynchronous programming is. I like this analogy with the restaurant, right, where a single chef in the kitchen let's assume he can really only work on a single task at a time. So for example, he needs to bake potatoes. First he needs to chop them and then put to the oven and wait. Now of course it's very inefficient if he's not doing anything while he's standing near the oven, right? He's probably actually in reality doing something else, like chopping salad or something like that. And this is what asynchronous programming is about. You have to, while you are waiting for some results that you've asked for previously, you're now switched to do something else. And basically there are many different methods to express the asynchronicity nature of software such as that. But before touching on these methods, I'd like to briefly introduce the concept of executors, which is quite important. We need to understand what actually runs the code that even though it's asynchronous, we need to understand what actually runs this asynchronous code, at least the synchronous portions of it. And the way I refer to the concept of the executor may be a bit abstract and conflate a lot of stuff together, but today I'm just interested in assigning a name to the thing that I mean to talk about. So if I put a task, a function, into some sort of task manager, I expect this task manager to obviously run the task, and that task maybe will schedule more tasks. And by doing that, my program will essentially move forward, right? Oops, sorry, 1 sec. So the one example of the executor could be something like a thread pool, or even a single thread. Another example is an event loop, for example, and we see many different event loops available in languages such as Python, C#, JavaScript, but in C++ out of the box we don't have anything like that, unfortunately. The three techniques that I wanted to discuss today are callbacks, future promises, and fibers and/or coroutines, because they can be used together. And so basically we see here a function that illustrates what we are going to do. There are synchronous portions and asynchronous portions. And the first technique that we are going to look at is callbacks. And of course, the problem with callbacks is the callback hell. If you happen to use callbacks very sporadically, it's not a problem, it's fine. But if you have a process such as on the previous slide, where you have to asynchronously go to one thing, wait for the result, when the result comes back you go to another thing, etc., and 5 times like that, then you will end up with this. And we've been there, and the name is correct, it is a hell. So avoid that as much as possible. The code here is really very simplified. Actually, it is much worse, because what tends to happen is these callbacks are spread across files also, and so the debug experience is really quite miserable with this approach. Now, the other approach is futures, which is, hopefully you are all familiar with what future promise is, but basically it is a very good chance to flatten your code base, right? So it is exactly the same code, just expressed with futures now instead of callbacks. And you can see how smaller it became and how much more synchronous-like it became. And I intentionally didn't use std futures here. It just says future, because you have to understand you can use std future, which is based on synchronization primitives like mutexes, so you largely depend on threading to to maintain the progress of your program, but features can also be based on fibers, for example, and that's what we are using in Nucleus today. I also wanted to briefly touch on coroutines, which we tried to use, but I only have 3 minutes left, right? I will try. So here's an example of a coroutine from Python, right, where we try to map an IP address to a country, but the databases that we have only can map IP address to a particular location, then we can map location to location ID, and then finally location ID to the country. For example, it's just an example. In Python, we can easily express this with async await syntax, and we can so the code actually looks very much synchronous, but actually it is asynchronous, and you can, in the main function here, you can schedule many different IP addresses, and they will all work together, even though Python is a single-threaded environment. So in C++ 20, they've introduced coroutines, and the code that I showed previously looks with coroutines something like that. Now, the problem with coroutines in C++ is that it is quite typical for a C++ committee to introduce a feature that is not fully ready to be used in production. And what I mean here is, really, it's just a syntax and the compiler support for breaking your coroutine into, basically turning it into a kind of state machine. Everything else is on you. There is no event loop like in Python or C#. You have to implement it yourself, and then you have to marry the syntax of coroutines to whatever the executor that you've implemented yourself, right? And so we've done it. The main problem with coroutines in C++, unfortunately, is debugging experience. I would put it that way. So we even visited C++ committee back in 2020 in Prague and addressed these problems, and hopefully they are addressed by now. But the problem was basically that coroutines are unlike functions. They maintain their state inside themselves, inside the coroutine handle object. This is the thing that manages the state of the coroutine, in particular where it is in its execution. Across all its suspend points. And debuggers didn't really like coroutines back then, and the year after still, I checked, where locals, for local variables for coroutines were not visible. And so, yeah, hopefully it is addressed by now. I actually had more slides about coroutines, but we have to continue in the Q&A session. If anyone is interested in coroutines, feel free to ask, but right now I don't have enough time anymore. Thank you.
Thank you. Sorry for the interruption. So yeah, in fact, we can talk forever, right, about asynchronous programming and coroutines. But yeah, we'll have a Q&A session, and I think we will have the chance. Thank you very much. So switching back to Armenian. Պաստորեն մենք համակարգային ծրագրավորողներս, ոնց որ ոչ միայն կոմպիլյատորներ են գրում եւ նմանատիպ բաներ, երբեմն պարզապես պետք է ինչ-որ բարդ համակարգ նախագծել. Եվ այստեղ մենք հենց գործ ունենք ինչ-որ բարդ համակարգի հետ, երբ խնդիրները այնպիսին են, որ երբեմն կարիք է լինում դիմել, ասենք, լեզվի ստանդարտը մշակողներին եւ ասել կլինի փոխեք, որովհետեւ ասենք մենք չենք կարողանում մեր խնդիրը լուծել։ Կարծում եմ, որն է, մաղթում եմ ձեզ, որպեսզի ունենաք այդպիսի խնդիրներ, որոնց լուծման համար կարիք լինի լեզուն փոխել կամ ինչ-որ նման մի բան, այլ ոչ միայն օգտվել։ Մենք